Hi team, if you're here, hopefully you're interested in expansion tanks. I've decided that I'm going to make a video today about how to select and pipe expansion tanks for institutional buildings for hydronic systems. I've noticed in my experience that these are often done incorrectly and that there aren't a lot of video resources out there about how this should be done from a design perspective. So this video is definitely aimed mostly at consulting engineers who are putting these in their hydronic schematics, but hopefully it's useful to contractors and commissioning providers as well. Everything in this video is just my opinion, product of my experience, so I'm looking forward to hearing your feedback and hearing what you might do differently. Hopefully this has some value to you. All right, so I'm going to break this video up into a few parts. First, I'm going to talk about the different types of expansion tanks on the market and talk about which ones make the most sense for our application. Again, primarily large institutional buildings. Then I'm going to talk just briefly about where in the system you should put it. And then from there, I'm going to start talking about piping details. So as an engineer, I, of course, mostly pick on engineers, and this is one of the areas that I see a lot of the problems that we're trying to address. And this should be a fun part of the video because we're going to look at some drawings, take a look at the details that we see, and then we're also going to get out on site and go take a look at some real world installs and talk about some of the pros and cons. As part of this section, I'm also going to talk about commissioning of expansion tanks. It just makes sense because we're going to be out on site looking at them. So we'll be able to do some tests and show how to apply a precharge to a tank. We'll talk about what that precharge should be and how to test it. All right, so to talk about the different types of expansion tanks, we're going to start on Amtrol's website. This is not an endorsement of Amtrol. It just happens to be that this is a manufacturer that I've leaned on a lot for my specifications because I'm familiar with their website and because they put the product information really front and center. I think for the same reason, I see Amtrol's expansion tanks being specified by our consultants more commonly than other manufacturers. However, I'm not totally sure what the sales side of that looks like because I certainly do not see Amtrol tanks on all of our installs, even if they're spec'd. And I have no problem with other manufacturers. We've seen Armstrong tanks, Wessels as examples, but not that concerned. So on the website, you can go down here. We're currently in the commercial section, and we're looking at hydronic and chilled water tanks. But a lot of what we're talking about today applies for plumbing and domestic hot water as well, but we're not going to talk about it in as much detail. As you enter the main section of their website for hydronic expansion tanks, you'll see here that they list the 3 different types of tanks that they've got: diaphragm tanks, full acceptance bladder design, and these partial acceptance bladder design tanks. And on the left here, they've got a bunch of information. And in my case, I usually am just looking at these manuals and submittals as they've got most of the important information that I need. However, today, we're actually going to look at the brochures a little bit more as they've got some visuals that will help our discussion. All right, so we're going to click into the brochure section of the Amtrol website for their hydronic commercial line, their extra tanks. And right off the top, we're going to see that they've got a nice cutaway of a diaphragm expansion tank. And this has some features which are specific to diaphragm expansion tanks, but it's also got some features which are universal to all of them. So right off the top, you've got this system connection. So this is where your pipe from your hydronic system is going to connect to the tank. They've got some feature there that they believe adds value. And then as you go down to the tank, you can see they've shown water on the top half. And then down here, they've got their diaphragm, which is attached to the side of the tank. And this is installed in the factory. And as far as I know, this diaphragm is not serviceable, which means that if you blow it, you need to replace your entire expansion tank. In some applications, this is going to be okay because your tank is small and easy to get out, and these tanks are going to be cost effective compared to other models. But in other cases, that concession is not going to be worth it as you get into larger tanks. And in the type of buildings that I work in, these are often not going to make sense on our primary hydronic systems. And I'll talk about that a little bit more in a few seconds. But as we go down through the anatomy of the tank, we've now got the air side below the diaphragm. And here you've got, they say, convenient air stem location. This is a Schrader valve under this little plastic cap. And so you can pump this up with an air compressor and increase the pre-charge of the tank. I believe most Amtrol tanks can pre-charge to 12 psi. I think most manufacturers pre-charge to 12 psi, which is suitable for some systems, especially if it's like only a single story, but wouldn't be suitable for, say, if you're in the basement of a multi-story building. This tank is base mounted, which is fine. But I think probably a lot of us, when we think of diaphragm tanks, are going to be thinking about the little inline ones that hang off the pipe. So I've just switched to their residential line. And here you can see their little extra tank that you would just be supporting off the pipe in most applications. I think they have mounting brackets. They also, so you can look at this on their website if you're interested, and they've got some little piping details. And I think for the scale of tank, this makes sense, especially because you might just drain the entire system if you had a small one like this. Going back to the commercial ones, though, we'll talk about the next downside of diaphragm tanks, which is their acceptance volume. So you can see here that for a tank volume of 6.4 gallons, you're only getting an acceptance volume of 3.2. And even as you go up into larger tanks, you're going to see that it continues that your acceptance volume is like 50% or less of your total tank volume. So as you get into larger systems, these tanks are going to get very large. So typically, I would not recommend diaphragm tanks for hydronic systems in large buildings because they're not serviceable and because the tanks are going to get quite large in a hurry. Of course, there's exceptions. For example, we often need to, on like makeup water systems or for like lab non-potable loops, we might have like a small plumbing system that needs to be isolated by a backflow preventer. So therefore we need an expansion tank for that. And that could be like as small as one room. And so using one of those little inline tanks for the plumbing application that's got the correct certification would be suitable. But again, for large hydronic systems, these aren't typically going to be the. So scrolling down a bit further, we can get down to their full acceptance bladder tanks and their partial acceptance bladder tanks. I'm just going to talk about the partial acceptance bladder tanks first. This is a tank that does have a serviceable bladder, so that's a pro for it, but it does not have a full volume acceptance. You can see here that the acceptance volume for many of these tanks is like 50% of the total tank volume. For that reason, I'm not certain where this makes sense. But to be honest, I'm not totally familiar with the cost difference. So I would not be inclined to specify these tanks. But if anybody has any feedback on why they do make sense for some applications, please put it in the comments. I'd like to hear about that and open up that discussion. So for that reason, for most of our hydronic systems, I'm going to be looking at a full acceptance bladder expansion tank. And what you can see here in this little image is that you've got a hydronic connection at the top, and then you've got this bladder that surrounds it. And depending on the manufacturer, the system connection might be on the bottom. That some of them, I think, might even be able to do bottom and top. Some of them, the bladder's like kind connected by the bottom, but then it's suspended off the top. It's worth looking at whatever model you're specifying or is being installed on your project to understand what the connections are. One thing that I think is really important to look at and understand is that there's some features that they all have. So the first thing, they're all going to have a pre-charge Schrader valve. And this is important for the contractor to use this to adjust pre-charge based off of what your system pressure is. And then they're all going to have a drain plug on the bottom somewhere. That drain plug, though, is on the air side of the system, meaning that if you were to remove that while the tank was pressurized, it could potentially be dangerous because you'd be releasing a large volume of compressed air. And I'm going to talk about this a bit more in piping details, because I have seen where some engineers show a drain valve installed on that. So some contractors have, at the request of the engineers, removed the plugs. And yeah, so just as a wrap up, the big thing about expansion tank types for me is that in most of our institutional buildings, we're going to be looking at a full acceptance bladder tank. And when I see other tanks specified, I'm always going to question why that decision is being made. And so I hope you do the same on your projects. And now we'll move on to start talking about where in the system we're going to put these tanks. All right, thanks for sticking with me. So we've talked about the different types of expansion tanks on there and my preference to go with full bladder ones. The next thing we're going to talk about just very briefly is where in your building you're going to put these. Now, the ASHRAE handbook has a detailed formula for how you're going to size your tanks, and I'm not going to spend too much time going into that. I think engineers are good at calculations, usually. But what I am going to talk about is one of the important practical results of those formulas, and that is that if you have a tall building, you can make your tanks a lot smaller by putting them in a penthouse mechanical room or near the top of the building. And I think the way that works out in the formulas is basically that your pre-charge is, of course, going to match your system pressure, right? And so if you're in the basement and say you've got a 150-foot building or something like that, then you're going to end up running your system pressure in the basement around 70 psi. If you pre-charge your tank in the basement to 70 psi, then it's obviously going to be very full of high pressure air. And then if your pressure increases in the system by, say, 10 psi, then not that much water is going to be able to go in there. And so you're going to have to see significant increases in system pressure before you're going to see the acceptance volume being used. And so it's not that usable for you. And so as a result, you need to oversize your expansion tank substantially. Now, in that same application, you go up to the roof, and if you had 70 psi in the basement and you're 150 feet tall, you're going to be somewhere in the range of 15 psi up there. And so suddenly, your pre-charge in the tank would be 15 psi, and your minimum operating condition. And then if your pressure increases by 10 psi in the system, it's almost doubled as far as what the expansion tank is seeing. So a large amount of that acceptance volume is available to you. That's how that ends up working out. And that's why, if you can, you want to put them higher up in the building. But again, it's really going to depend on your application. And as much as there are cost savings to be had here, there's also going to be advantages to putting it in your basement where it might be more serviceable. The leaks might be more manageable if you had any. And I don't think that in the type of buildings that I'm thinking of anyways, that expansion tanks are going to be a major driver of project cost and are probably not the low-hanging fruit of value engineering. We'll probably talk about this a little bit more and where specifically in the system they connect in a few seconds as we're going to start talking about piping design. All right, team. So I went ahead and I pulled out some excerpts from a couple drawing sets. I made a point of selecting projects over the last 20 years and from different consultants. So just to try and show trends from the industry as a whole, rather than showing any single case. I want to stress that this is something I'm trying to improve across the board. So the first one that we're looking at here, you can see that we've got an expansion tank showing. In this case, if you were to look at the way it's drawn, it looks like it might be a bladder style tank, but in actual fact, looking at the O&M manual, it is a, it's drawn to look like a diaphragm style tank, but it is actually a bladder style tank that was installed on site, which is great. So I like that. But the problems I've got with this are that there's no drain valve here. So you can isolate the tank, which is good, but then if you want to check the pre-charge or do any service on it, you need to crack the union and spray water everywhere. I guess you could get clever, and with the way this pressure gauge is piped, you could spin off the pressure gauge and then open the valve, isolating the pressure gauge, and maybe you've put some kind of adapter so you can take that to drain. But really, there should be a drain valve, ideally piped to a floor drain. And then this is interesting, and I've seen this on a few of our installations on site here, but they show a drain valve on the bottom, and this drain valve, it's not shown super clearly here, but that's this. And typically these expansion tanks ship with a plug there, and I'll show you on site that they're labeled "do not remove." That plug is on the air side, and so I don't think you want to put an isolation valve there, because really you would only be pulling or want to open that in the case that you'd had a blown bladder that you were trying to replace. And you certainly don't want somebody accidentally opening that, because at best you're going to quickly remove your entire pre-charge from your tank. And at worst, you're going to have like depressurization of compressed air very rapidly, which can be dangerous depending on how high your tank pressure is. So that's one. Here's another one from another job. In this case, we have a glycol feeder. So similar to a makeup water connection, this is kind of a whole other discussion, is how you pipe makeup water to a system, and maybe I'll do a video on that one day. But what is relevant here is that you've got your expansion tank piped directly to your system, and it's good. It's connected to the inlet of the pumps, as was that one. But I can tell you, if you zoom out and you look at the rest of the schematic, there's no way to isolate this tank without going potentially quite a way out into the system. So you're going to need to drain quite a bit of your building simply to service your expansion tank. So that's not good. You really need to have an isolation valve here and the drain. And here's another one. This is an older job. Again, I do have some concerns about the way that the makeup water station's done and the lack of a PRV here, but that's not a discussion for today. But I just want to highlight that we're showing an expansion tank, and there's no isolation shown for this expansion tank at all. In this case, I'm familiar with this building, and I think we do actually have it installed on site. So it's maybe it was shown correctly in a detail on the drawing package, or maybe the contractor just fixed it up or picked it up and did it correctly. But regardless, definitely an issue there, and I think there's an opportunity to improve all these. So now I'm going to go out onto site and show you one of these systems that doesn't have isolation installed in the wild. So I'm here in one of our buildings and just looking at an expansion tank, and I want to highlight a couple things about this one. So this isn't such a great install. Let's start with the makeup water. So we've got makeup water, that's relatively normal, backflow preventer, PRV, pressure gauge, isolation valve, and then it comes across. This takeoff goes to the tank, and this takeoff goes to our system, and presumably there will be eventually another isolation valve there. But as far as the tank itself goes, the problem is that if you isolate it, I don't have any way to drain the tank. So I need a drain valve along this pipe, or a pressure relief valve, but at least a drain valve, so that when it's isolated, I can drain the water off, because without draining the water off, I'm not able to check what the pre-charge is or do any service. So if I was servicing this right now, the only choice I would have would be to close the isolation valve and then crack the union and let it spray water everywhere. Now, this is how you charge. You set the pre-charge in this one. So ideally, whoever installed this however many years ago would have written the pre-charge here that they did. Just see. So water or air, so that's good. So at least we don't have a burst bladder. Just back here looking at this one more time, and I just want to show you one more thing, is that this cap's going to allow you to, if you undo all these bolts, to pull the entire bladder out. And then down here on the bottom, we've got this drain plug, which is labeled as do not remove. And I think in some of the other installs that I've looked at, I've noticed that there was a drain valve on that, which I do not encourage, because I believe that that's on the air side of the tank. So you wouldn't want to remove that until the system was completely depressurized. And an example of where you would move that is if you knew you had a blow-in bladder and you needed to replace it. What's going to happen is you drain the tank, but or you from any overpressure condition, you depressurize the tank. But of course, if the bladder's blown, it's just going to stay filled with water. And so you need a low point drain, which would be that guy. So you would have to do the low point drain, get all the water out of it, and then pull your bladder off the top. Replace your bladder and put it back together. Pre-charging, of course, as you go. All right, so now that we've looked at an example of what not to do, let's take a look at some examples of how we can do it and make it look pretty good, because some jobs are done well, some are done perfectly, and others get some of the elements right. So again, this is all just my opinion, but these are elements that I think add to it. So this one here, it's actually done pretty well. I really like that they've got a nice symbol that's descriptive of the type of equipment they're using, being a bladder style expansion tank. Very, very nitpicky. They could have shown it actually connected at the top there. A significant part of my day job is that I review drawings, so I can't help myself when I see these but to paint them in red. So, 2 pressure gauges, no problem with that, but it is redundant. I'm not really sure why there's an auto air vent here, or maybe that symbol's supposed to be something else, but it's fine. It's not really hurting us. But what I do like about this one is we have an isolation valve here, and that we are able to use that isolation valve to isolate the tank. And then we have a drain valve here. So you can then drain off any fluid that's in the pressure, depressurize it, which then means you can measure your pre-charge and then top up your pre-charge if needed, or you could replace the bladder, do any service you need. The only thing is that it would be a lot better if we had an additional valve at this location. You may or may not even need this first one, but it's probably good to have, but an additional one here, because that way you could isolate the tank, but your pressure relief valve would still be connected, which is great because you're still protecting your system from an overpressure condition somewhat. So good detail, but could be better. Over here, we've got one that's even better. So this, to me, is an ideal piping. We've got a fill line showing, so hopefully somewhere else in the package they show the backflow preventer and the PRV associated with that. I know this job too well, so I do know that there were some issues upstream where we could have shown that better. But hey, let's not worry about that because that's outside the scope of this discussion. Here we've got a relief valve, but it's upstream of our isolation valve. And then we've got our expansion tank, and we've got a drain valve, and they could have put a little note here that this goes to drain, but I think that's pretty obvious. And they actually even noted what they want the pre-charge to be in this case, 15 psi, and that's a logical number in this case. We're connected to the inlet of the pumps, and this expansion tank is located in a penthouse mechanical room at the top of the building. So everything here makes sense. The only thing I would do differently, and it doesn't really matter, is that I look at this symbol and I think it's a small diaphragm tank, whereas in reality this is a relatively large bladder style tank. So minor detail. Because schematically it's shown right. And I think from a desk jockey perspective, which is really what this is targeted at, that's how I see myself, I think we're doing really well here. So good job to whichever consultant did that. And then down here, this is kind of my little Bluebeam stamp that I've put together that I often share when reviewing jobs. And actually through putting this video, I've added some more details to it about what I like to see. So again, we've got our system connection, whatever that looks like, with the inlet of the pump, commonly your makeup water connection is going to be right here as well, the pressure relief valve, and then an isolation valve. And and then we've got our connection to the tank. But before that, we've got a drain valve. We've got both of these manual valves should just be quarter turn ball valve isolation valves. We've got a pressure gauge here. I noted that we should put a pressure gauge and a Pete's plug. I always like to see little neoprene test Pete's plugs, or Winters calls them test ports, because over time pressure gauges are not reliable. I've got a symbol that conveys that it's a full acceptance bladder style tank. This is one that's got a top connection with this tube that goes down. And then I've got a little note here to pre-charge the tank equal to the minimum system pressure. And this is something I've never seen, but I would love to start seeing our contractors provide a label indicating the pre-charge pressure, the date, and the initials of the person who did it. The best we see is that contractors commonly will, under the cap here, they will in Sharpie write the pre-charge pressure, which is a lot better than not doing that. And I would say if you pull that cap off and there is not a Sharpie saying the pre-charge pressure, I would be very suspicious if it was charged. Down here, we show the drain plug, which again, you just are going to leave in place. You would only ever remove that if the bladder's blown. So yeah, we're going to go to site now, and we're going to take a look at an install that does all of these things actually really well. And then we'll come back and regroup at the.
All right, guys. So I'm here, and I've been just checking out expansion tanks so that I can talk about what's piped well and what's not piped well on them. And I've just came into this building and looking at what I think must be about the best expansion tank piping detail you can have. A couple very large expansion tanks, and just gonna start up here at the system connection. See, we got the system connection, we got a pressure relief valve, and then we've got a pressure gauge, which is great, so we can tell exactly what system our pressure our system's running at. It's saying 16 psi, which seems very reasonable because take that back. 18 psi, very reasonable given that we are in the top floor of this building. And then we've got our system makeup connections coming in here, which is, just very neatly piped. I like the rack. I like the way it's done. I should add too that both of these tanks can be removed to the opposite side. There's a walkway that goes around this, so it doesn't get much better than this. But we've got our system makeup with our PRV. We've got a meter on it, which is great. Going back to the building automation system. And then we come down here to the tank. They have removed the handle from the isolation valve. There's a concern among many consultants that maintenance workers or other personnel in the mech rooms might isolate the tanks, but the handle's there, so that's fine. And then there's a drain here. So if we had any concerns about this tank, what we would be able to do is close this valve with that handle, and then we'd be able to drain off the pressure, and we'd be able to inspect it that way. But then also here, what you can see is this one I'm pretty sure is a bladder style tank with two connections. There's a connection in the bottom right there, and there's also a connection, or there could be a connection at the top. I think if you really wanted to, you could probably use that connection. Some manufacturers have their connections only on the top and they don't have one on the bottom at all, but probably more likely would be that you're going to use that as your water connection on the bottom, and then if you ever needed to replace the bladder, you can remove that connection, remove the jam nut that's holding it on, and then you can pull the bladder out of the top. And there's actually a cool video from one of the other manufacturers showing how to do that, and I'll make sure to link that as well.
All right, guys, what we're going to look at next is how we can check to ensure that the pre-charge in an expansion tank has been set up correctly. Now, what you need to understand is that if your system pressure exceeds your pre-charge, and then you attempt to measure the pre-charge at the Schrader valve, then what you are going to find is that your system pressure matches the air pressure in the tank. And the reason for that is If your system pressure is higher than the precharge, then water will flow into your bladder until the pressures equalize outside the bladder and inside it. So the first thing you need to do is you need to isolate your tank, and then you need to drain it. And so, as we've discussed a few times in this video, this is why it's so important to have that drain valve. So you're going to drain your tank, ideally by opening a drain valve if you've got one, or pull a pressure relief if you've got one, or finally, worst option is crack a union and spray water everywhere. Or I guess worst option is really cut a pipe. And so in the video we're about to watch, me on site, what I did is I had an isolation valve, and in this case I had a pressure relief valve. So you're going to see me isolate the tank. I'm then going to open pull the pressure relief valve until all the water drains out. Once water is no longer coming out of the tank, I'm going to check what the pressure in the tank is. In this case, the tank actually has a pressure gauge on the air side, but I'm going to validate that with a pressure gauge, like a handheld pressure meter, like a tire pressure meter that I push up against the Schrader valve. And then I'm going to, once I've validated that we do indeed have a precharge in this case, I'm going to put everything back and let it fill up the tank. One thing I talk about in this case is that you'll see the results here. We do have precharge, but it's surprising that the precharge is as high as it is. Typically, you want to run system pressures as low as possible. We're on the roof of this building, pipe to the inlet of the pump, so 15 psi or so would be a very typical value, and we're seeing 40 in this case.
So this is where the Schrader valve is going to be for pre-charging the tank. Hey team, so I just want to really quickly go over the procedure for checking the pre-charge on an expansion tank. This is on a chilled water loop in one of our buildings, and I noticed that the expansion tank is reading a pressure of about 45 psi, which is a bit high considering that this is piped to the inlet of the pumps on the top floor of this building. We're seeing basically the same pressure at the pressure gauge at the inlet. What we're going to do is we are going to close the upstream isolation valve. So there we go, the valve is now closed. And then we are going to drain the tank. In this case, we are going to use this pressure relief valve that's here. Ideally, we'd have a drain valve that we could open because we don't like using pressure relief valves for this application because they don't always seat perfectly. So we can do that, and we'll feel that there's quite a bit of flow coming out. The other problem with relief valves is you need to hold them open, and it's a bit sore on your fingers, so I'll come back when this is drained completely. All right, so I'm back just a minute later, and we can see that our pressure has not dropped substantially since I opened the valve and drained it. And so that's a good sign, because that suggests that we've got a decent precharge there. Probably that would be the precharge. We'll put our pressure gauge on here, and we're gonna read 38 psi, which, hey, close enough, I'll take it. So now what we're gonna do is we are going to open the fill valve, and we're gonna let it fill back up and see where we end up.
All right, if you're still here, thank you so much for spending some time with me. Obviously, this isn't the most riveting content on YouTube, but hopefully the technical information that I've provided here has got some value to you. Got some key points that I'm just going to have to go over really quickly. First off, just make sure you select expansion tanks that are suitable for your application. You guys need to determine what this is, but in my experience, when you're working in large buildings, this often means that you're going to be selecting full acceptance bladder style tanks. Number two is locate your tanks in your buildings where the lowest minimum pressure exists. So often this means on the top floor. The advantage of this is that your tanks can be smaller, which is an advantage from a first cost perspective, but it's also an advantage from an operations and maintenance perspective, because if the original tank was cheaper, then a future replacement tank, if needed, will also be cheaper. And smaller tanks are easier to maintain because we can test them without having to drain a large volume of water or, again, replace a relatively small bladder. Most important point is make sure you pipe all expansion tanks with an isolation valve. And then between the isolation valve and the tank, you've got a drain valve. Ideally, that drain valve is going to be piped to a floor drain, but alternatively, just put a hose bib connection on it and a maintenance worker can come along with a hose and then they can drain the tank themselves. Fourth thing is make sure that your tanks have been pre-charged appropriately by your contractor. I showed in this video how to test that. I know that's not going to be realistic for most of our consultants, but you can look for a marking on the tank that indicates what pressure was pre-charged. You can question your contractor on it, and if needed, you can have them demonstrate that to you. And finally, use symbols in your drawings that convey the function of the tank. And I believe this to be true across all components of your mechanical systems. If you show the bladder and you show how it's piped internally, it's going to help your junior engineers, your technicians, as well as site personnel understand how the devices function and how they're supposed to be set up. All right, I've had a lot of fun putting this video together. Something I've been thinking about doing for a while, but it is my first YouTube video, so it was a bit of an undertaking. Hopefully you guys got some value out of it. I'm looking forward to getting some feedback in the comments. Definitely let me know things that you would do differently. I'm sure that there's going to be some disagreement about this. I'd also love to know where people are using those partial acceptance bladder tanks, and if people disagree on my preference towards full acceptance bladder tanks opposed to diaphragms for institutional buildings. So yeah, just put that down in the comments. And if you are interested in more content like this, please note that too. And if you've got any ideas, you can put them in there. I've got some ideas of my own, so I'll see how the reaction to this video is and see if I can maybe put together another one in the next couple of weeks. Until next time, thank you.